Okay, so you might have got into a few questions that mentioned something about the coefficient of friction. Okay? The coefficient of friction is a number that describes how, essentially, sticky is not a great word, but how easily two surfaces will slide past each other. Okay? The higher the coefficient of friction, the harder it is to get them to slide by each other. So rubber on asphalt would have a very high coefficient of friction. Okay? Those two surfaces don't slide past each other easily. Teflon against ice would have a very, very low coefficient of friction. Both of those surfaces are very slippery, okay, when put together. Okay? That sort of makes sense? Okay? So for friction, okay, friction is dependent on two things. Okay? You have a formula that looks like this on your formula sheet. You probably went looking for it yesterday if you got that far. Right? And it says that force of friction equals mu, that's the coefficient of friction, times the normal force. Okay? So two things then can affect how much friction is present when two objects or surfaces are trying to slide by each other. The coefficient of friction between them, mu, and how hard they're being pressed together. Okay? So, easy example. If I just try and slide this desk right now, is it pretty easy to slide? Right? Like when you're moving desks on exam day, right? Like you pick them up and if you're dragging them, you drag them like this. Okay? You don't try and do this. Like, because that's dumb. Okay? Why would I try and do, why is that so much harder than lifting and dragging? When I push down on the desk, what does the floor have to do? It has to push back harder. Is that this force? Yeah. So if I do anything that increases normal force, increases the force of friction. Who else in here drives a pickup truck? Really? Okay, there, thank you. Okay, what do you do in the winter? What do you throw in the back? Or are you brave? Weights, yeah. Okay, like I go out, and in fact I was going out tonight to do it because it made me think of it yesterday when it snowed the other day. I go out and I buy bags of like sand or softening salt or something heavy, right? Then I throw 4 or 5 of them in the box of the truck. Because that puts weight on my back wheels, because trucks are rear wheel drive. Okay, so I put that extra weight on the back wheels, and then the ground has to push back against my tires harder, and it increases the friction between my tires and the road, even if it's slippery. It comes at the cost of fuel economy, because now I'm carrying around an extra 250 or 350 pounds, but it helps when I need to get going. It doesn't help me stop as much. I mean, yes, there's more friction because my truck is heavier, but there's also more kinetic energy that has to be gotten rid of as well, okay, because my truck is then heavier. But that's the reason we do that. Putting extra weight in our truck or our car or whatever it is we drive, it increases the normal force. The harder the two surfaces are pushed together, the more friction there will be, the harder it will be for them to slide. Okay? It's also why when we walk on ice, as people who have experienced winter more than one time in our life, when we set our foot down on the ice, we know it's going to be slippery, so we keep our weight over our feet as much as possible, because that increases the normal force, and thus the force of friction on our feet. If we're leaning or pushing at angles and it's a slippery surface, there won't be as much friction, and we're more likely to slip and fall. That sort of makes sense? There's lots of applications for friction. Okay? The other thing that can affect the the force of friction is the coefficient of friction. It's just the nature of the two surfaces. Okay? If the two surfaces are slippery, that number is going to be very low. All right? What do we do in Canada to try and change that number? How many people have a separate set of tires for winter? Okay? Having a separate set of tires for winter can help that a little bit. Okay? Because what winter tires do is they're first off made of a softer rubber, which is why you don't want to drive on them in the summer. They'll wear a lot faster. Okay? But they're made of a softer rubber that remains pliable even in cold temperatures. And if you've ever noticed, if you look at winter tires versus summer tires, the traction blocks on a winter tire have a whole bunch of little squiggly lines on them that summer tires don't have. Those are called sipes. And what they do is because the tire remains flexible, even in cold temperatures. As your car's tire hits the ground, those sipes open. And because water is a polar molecule, any ice that you've melted due to the heat of your tires or the spinning of your tires can be pulled into those sipes, and then as the truck or the tire rotates, it's thrown out behind the tire. So it pulls the water away and makes it so that it's not lubricated between the tire and the road, and you get better traction. Right? Does that sort of make sense? Okay. So there's things that we can do to change the coefficient of friction. That's the nature of the two surfaces, and things that we can do to change the normal force, how hard those two surfaces are pushed together. Okay. Another kind of easy example of that would be like on a desk. All right. So if I put this book on the desk, it's pretty sticky, right? It's not going to go anywhere. The desk has a very small angle of incline, you've probably noticed that. Right? Now, if I change the incline of the desk, okay, still not sliding, is it? Okay, so there's enough normal force here to still hold it in place. The coefficient of friction hasn't changed, right? It's still the book and the desk, agreed? But eventually, I'll get it steep enough that it'll start to slide. Okay? At that point, what's happening to the normal force as I lift and change the angle? It's getting smaller, right? When the desk is flat, normal force and gravity are equal, right? They're equal. One pushes, the desk pushes straight back up with the same amount of force as gravity is pulling down. But when you start to angle it, so like on an inclined plane, which is what you would have run into yesterday, okay, we talked about how this little triangle inside an inclined plane, where this side's the force of gravity, this side is F parallel, and this side is normal force. Up until today, we never had to use that for anything. Okay? But as this angle, which is the same obviously as this angle, as that angle increases, what's going to happen to the length of this line as this angle increases? It's going to get smaller and smaller, and this number is going to get bigger and bigger. So the steeper it gets, this number gets bigger, this number gets smaller, and pretty soon F parallel is stronger than the force of friction, and the book starts to slide. Okay, so in this case here, where it's not sliding yet, F parallel and the force of friction are, come on, I'm an old man, I can't hold this desk much longer. They're equal, because the net force is what? 0. That thing's not moving, right? The book's not moving, there's no acceleration, net force is 0. But eventually I'll get to a point where the normal force gets so small that when multiplied by the coefficient of friction, okay, the force of friction is too small to counteract the force parallel, and the book will start to slide down the ramp. Okay, everybody all right with that idea? All right, so how do I calculate normal force on an inclined plane then? Cos. Yeah, okay. It's still this triangle. This triangle is never going to change. F parallel is always going to be the opposite side, and normal force is how hard the plane pushes outward. Okay? It's always going to be the adjacent side. Right? So all you need to remember is that, well, you don't need to remember it, it's on your formula sheet. Force of friction is coefficient of friction, mu, times normal force. Okay? That'll get you the force of friction. To calculate normal force, well, you've got to look at the other forces involved. If it's a normal surface, okay, it's level, there's no other forces involved, normal force and gravity are equal. Okay, if it's an inclined plane, it's the adjacent side. Just got to calculate it. What if I have a situation like this? I've got a box on a level surface, but I'm pulling it at an angle. Are normal force and gravity equal now? If I'm pulling it at an angle, I'm pulling it both to the side and up. So that would be like this then. I'm lifting the desk. Is all of the desk's weight on the ground now? Right? I'm pulling it at an angle. right? It's not perfectly horizontal, I've got an angle. So if I'm pulling it slightly upwards, there's a vertical component here. That means some of this number is here. So normal force isn't as big, which is why it's easier to drag the desk by lifting and pulling than just by pulling. There's less friction because I'm holding some of the weight off the floor. Does that make sense? These are all things that we kind of understand practically because our instinct is, well, it's easier, so we'll do it this way. Nobody pushes the desk down the hallway. Well, maybe somebody does, but then I'll catch them and I'll explain to them why that's silly. Okay? But yeah, most of us instinctively will not do that. We know it's easier and that there's less friction if we do it that way. I mean, why do you think they put those tennis balls on the bottom of all the feet? You ever notice that most of the desks have a tennis ball on every foot? What part of that formula does it change? Changes mu. Yeah, changes the coefficient of friction. Those tennis balls are way more slippery, so it doesn't make noise as much. Okay? When they just had the regular feet, they make tons of noise. Okay? And they marked up the floor. Okay, making sense? All right, so friction is dependent on those two things. All right. So this is that person doing it wrong. Okay, if you're pushing down on a desk, trying to move it forwards, okay, your force applied is this direction, which means there's a vertical component to that force and a horizontal component to that force. But the vertical component is adding to the normal force, right? Because you've got the gravity of the desk plus the force applied vertically downwards. Well, normal force has to balance both of those. So it's going to be bigger than if you just pushed it horizontally. Okay? Everybody all right with that? We don't do a lot with this because it's just kind of more practical than it is anything else, but you still need to understand how this formula works practically as opposed to mathematically. Mathematically, it's pretty straightforward, okay? But you have to understand how it works from a practical standpoint. If I want to decrease friction, I need to do one of two things. If I want to increase friction, I do the opposite one of those two things. Okay, here's an inclined plane problem involving force of friction. Okay. I would like you to calculate for me first the force of friction in this problem if the 10 kilogram box is stationary. So it's not sliding. It's just been placed on that ramp. Okay. So somebody put the box on the ramp and it won't slide. Right? I want you to calculate for me the force of friction first as a first step. So on this question here, okay, the other force involved is the force parallel. Okay, now because it's not sliding, F parallel and the force of friction are equal. The force up the ramp and the force down the ramp have to cancel each other out so that the net force is 0. So have that internal triangle here. I'll have Fg on this side, which will be 98.1 newtons, 9.81 times 10. Okay, I'm going to have force normal. And I'm going to have force parallel. Right? Now to answer the first part of this question, all I need to do is find force parallel. Right? So F parallel will be the sine of 20 degrees times the hypotenuse of the triangle, 98.1. Okay, so that's going to be 33.55 newtons, okay, and then that means that friction will be 30, well, we only have, what, 2 significant digits there, so 34 newtons up the ramp. Okay, here's part B. what's the coefficient of friction between the box and the ramp? Okay, so remember, force of friction is mu, coefficient of friction, times normal force. Okay, I'll give you a minute or two on that one. Okay, so since I know the force of friction, okay, I already calculated that here, I need to get the normal force so I can solve for coefficient of friction. So to get the normal force, I'm just going to go cos of 20 degrees, because it's the adjacent side of the triangle, times the hypotenuse, not equals, times the hypotenuse, 98.1, okay? And so that'll give us a normal force of, cos of 20 times 98.1. So there's our normal force, 92.18 newtons. And then I just need to divide that by the force of friction. Okay, because if I'm solving for, sorry, I'm going to divide the force of friction by that. I'm going to bring normal force over here. Okay, so I'm going to divide the force of friction by the normal force. So there was my force of friction. But I'm just going to use 34 because this would be a part B. So 34 divided by that number there. Okay, so I get a decimal. Is that okay? Yes. Almost all coefficients of friction are a decimal. They're basically the percentage of the normal force that gets converted into friction. Okay? Friction is almost always smaller than normal force. Okay? So it's like a percentage. It's how much of the normal force actually can be converted into friction. Okay? So our coefficient of friction for that one is 0.37 newtons. Or sorry, 0.37. No units. Why are there no units? Why are there no units on this? It's what? It's a coefficient. And what did I divide to get it? Newtons by newtons. Yeah, I'm pretty sure they cancel when you do that, right? It's force normal divided by, or force of friction divided by force normal. They're both forces, so the units cancel. There's no units for coefficient of friction. Okay? All right, everybody okay with that? Hey, I mean, really, there's not much more to that formula than understanding that coefficient of friction and normal force affect friction in this way. All right, so here's the other way I could give you an inclined plane problem with coefficient of friction. Okay, so here's the coefficient of friction. This box is being pushed up the ramp with a force of 120 newtons. Calculate the acceleration of the box. If it gives you the force of friction, is friction present? Sorry, it gives you the coefficient of friction, is friction present? Yes. Okay, so I'll give you a few minutes on that one, then we'll walk through the steps. So, first thing we got to do is identify the other forces acting up or down the ramp, okay? And they're both acting down. One of them is the force of friction. What's the other one? Force parallel. It's always there. Whether the box is going up the ramp or down the ramp, it's a hill, and gravity wants to pull it down the hill. So F parallel is always there. Okay? So if I want to calculate the acceleration of the box, I need to find out what the force of friction is and what F parallel is. So that means I'll need all three sides of that triangle. Okay, so that'll be F normal, that'll be F parallel. Okay, this is going to be 25 degrees, and this is going to be FG, okay, which will be 196.2 newtons. Okay, everybody all right with that? I just went M times G, so 20 times 9.81. All right, so I've got to calculate normal force. Okay, so that's going to be the cos of 25 times 196.2. Okay, so that side's 177.82 newtons. And I've got to calculate F parallel. Okay, which will be the sine of 25 times 196.2. is 82.92 newtons. Okay, so this is 82.92 newtons. All right, I still don't know the force of friction, but can I calculate it now? I have normal force. The question gave me mu, right? So I can go force of friction is mu times the normal force. So that'll be 0.125 times 177.82. But I'll use all the decimals. Okay, so that's going to be 22.23 newtons. Okay, I've got my forces down the ramp, got my forces up the ramp. What do I calculate now? Net. Yeah, I need the net force because without that, I can't calculate the acceleration of the box. So 120 minus 82.92 minus 22.23 should give me my net force. That's up minus down. Okay, so 120 minus that minus that. All right, that gives me a net force of 14.855 newtons up the ramp. So now I can calculate the acceleration, F net divided by m. Okay, so divided by 20 kilograms, 14 points, what was it, 855 divided by 20. All right, so the acceleration of the box is 0.74 meters per second squared up the ramp. Okay, they really don't get much more complex than that, and it doesn't really change a whole lot. Sure, you got to calculate F normal, but you're just doing an inclined plane questions. Forces up the ramp minus forces down the ramp, and you're off to the races. Okay, everybody all right with that? Okay, that's generally what we need to know about the force of friction. Be able to use that formula mathematically and be able to understand how it works practically. Okay. All right. So it's my understanding then that we didn't get to the vector questions on that worksheet yesterday. Okay. I would like for you guys to circle these on your sheet. Anyone else not get the sheet yesterday? Okay. Okay, I would like you guys to do numbers 3, 4, 6, 9, and 11. Okay, so that's what I'd like you guys working on here. We should have ample time to finish those because tomorrow we're going to be doing a lab. Okay, and that lab will be just like questions 9 and 11, where you have masses and a pulley, and we're going to make it go. Okay. Oh, yeah, I didn't have any picked.
Okay.
I think everybody just kind of got as many done as they could. I'd say we can do every other one. Yeah.
is how much force is down the ramp minus how much force is pulling back up the ramp. So, you added them, but you made one of them. Oh, because you were looking for F parallel. So when you subtracted this force, it was up the hill. So it was subtracting negative. See that? Right, so you had F parallel, F net, which was down the hill. That's a positive. Minus a negative number. That's why you added. Does that make more sense? Yeah. you go to a diagram question 4? Okay, so. Fish. Okay, it's being pulled like this. It's a 45-degree angle. It says that friction's acting backwards in that question, right? Straight back, because the fish is moving straight forward. So if the fish is moving straight back, does this have a horizontal and a vertical component? So gravity must be offset by this. But it's moving at a constant velocity there. How does this force relate to that force? Yeah?
Okay, any of those giving us trouble so far, guys? Any ones we want to go over? Number 4, I kind of thought so. That's why I pick it. I'm mean. And forgetful. It's been recording the whole time. Okay, that happens all the time. What do we got here? Oh, we need the vector one. Number 4 on the vector one. Okay, so we've got this fish. I'm going to draw it over here. Now you know why free body diagrams are my friend. This is a very unhappy fish because it has a hook stuck in its face. Okay, and here's what we know. We know that the fish is being pulled at a 45-degree angle. Okay, and we know that the force of friction is opposing with a force of 80 newtons. Okay, I'm supposed to find the tension in the line, but it does specifically tell me that the fish is moving horizontally. Okay, so if it's moving horizontally, then the vertical component of this force must be balanced by gravity. Would you agree? Like they must cancel each other out because there's no vertical motion. But it also tells me the fish is moving at a constant velocity. Why is that important? There's no net force. So if the force backwards is 80, how much is this? 80. Can I find the tension in the line now? All that question is a, hey, remember those key words I keep telling you about? Constant velocity means no net force. That's what that question's about. Yeah, you got to do a little bit of trig. Okay, so you got to go, all right, I know the adjacent side. You actually know the opposite side as well because it's a 45-degree angle. Okay, but you just have to do the trig to get the hypotenuse.
Is friction always horizontal?
Friction always directly opposes the motion. That's why the question had to say the fish was moving horizontally. If the fish was moving this way, friction would have been this way. It would have made the question more difficult. That's why I stated that the fish was moving horizontally. Yeah? Does that make more sense? Yeah, it's not always horizontal. It's always directly in opposition to the movement. So in our lab tomorrow, we're going to have a setup just like this. Okay, you're going to have one of those carts that we've used already a couple of times in our labs, but this time you're going to tie a string to it. Okay, when there's actually a little hook at the front you can tie it into, and you're going to run it over a pulley to a hanging mass. We're also going to put some mass on top of the cart. Okay, we're going to make the whole system a little bit heavier. All right, and here's what we're trying to do. We are trying to find out the relationship between force and acceleration. Now, we might have already know that because we've kind of been working on Newton's second law for a couple of weeks now, okay? But that's what we're just trying to confirm. So what we're going to do is we're going to hang different amounts of mass over the pulley. But what we're going to do is we're going to take it from the cart. So in our first trial, we'll have a bunch of mass on top of the cart and very little mass hanging over the pulley. Right? So the mass that's hanging over the pulley is providing the applied force to move the system. Would you agree? So each trial, I'm going to take mass off the cart and move it over the pulley. what am I keeping the same that's really important by doing that? I'm keeping the mass of the system the same. I'm not adding more mass to the system. What I'm trying to find out here is what's the effective force, my manipulated variable, okay, on acceleration, my responding variable. Well, in order to do that, I've got to control the one other thing that can affect those, which is mass. If I change the mass of the system, this whole thing is out the window, right? So the reason we want to transfer mass from the cart to the pulley is because that will keep the mass of the entire system from changing. Otherwise, I essentially have two manipulated variables, and then I won't know which one affects the experiment. Okay? So obviously, as we move mass from the cart to the pulley, the acceleration of the system is going to go up because there'll be more force on the same mass. Okay? So obviously our acceleration should go up. And that's what we're going to try and graph. Okay? We're going to make a graph of velocity versus time so we get our acceleration, okay, for each trial. Right? You're not going to have to, like, you can show me the graphs, but we're not going to do much from them other than steal the slopes so we know what the acceleration for each trial was. Okay? Then we're going to use that to do some analysis of the effective force on the acceleration of the system. Okay? It's a pretty straightforward lab, really. Okay? The procedure takes a little longer because you do have to do a few trials, but once you get the hang of it, it's pretty easy. You're just hanging mass over a pulley and letting it go. Okay? And then letting the thing record the velocity of the cart as it moves along. Okay? Questions on how that's going to work for tomorrow? Okay? My hope is that you'll get a fair amount of the lab report / homework done in class. Okay? Friday's quiz is going to be Newton questions that are inclined planes, they involve friction, there's some vector stuff, okay? Because the first quiz was just collinear stuff, okay? This quiz is going to be more about vectors, all right? So expect that what's going to be on that quiz is very much like the worksheet you have in front of you, all right? So if you want to practice for Friday's quiz, any questions you haven't done on that worksheet, you should do. And then I think quizzes 3 through 6, the practice quizzes 3 through 6, I think are the ones you need to look at there. If it says Newton's third law, don't do that. Okay, we haven't gone over that yet, that's next. Okay, so that's what's coming up here, guys. I don't remember when I made that lab due, but I think I gave you until like next Wednesday, I think, to finish it, or something like that. It should be lots of time anyway. Then next week, to start off the week, we're going to do our assignment on Newton. I'll give you the whole class on Monday after we go over the quiz to work on that, so you won't have too much homework on that either. And in the last few minutes of class here, I'm going to figure out when your exam's going to be. And it's probably still 2.5 to 3 weeks away, but I like to give you lots of notice. Okay, so I'll figure that out, and then you'll have that date as well.